Several years ago, I made an attempt to photograph a partial lunar eclipse that was visible in my part of the world. Here you can see the result, with some success. But beyond the moon, there is space. How far can we go out in space? Does it go on forever? Is it infinite? Currently, with our technology, we can't get there. But in our mind's eye, we can perhaps imagine what infinity might be like. We can certainly apply the same idea to functions and ask ourselves, well, what is the behavior of our function out at infinity, or negative infinity if we consider the other direction? That's what we'll be discussing in this video. What happens to a function, in other words, the limit, as x approaches infinity or negative infinity? But before we go out to infinity, please remember to subscribe and like this video. Subscribing to my channel and liking my videos helps support this channel so I can continue to bring educational content to you, heading toward, hopefully, an infinite amount of content. Let's get started talking about infinity. In pre-calculus, we learned the n behavior model, which for polynomials says that given a polynomial f of x equals a, x to the n plus b, x to the n minus 1, etc., down to lower degree terms, if n is even and positive, f of x heads toward positive infinity as x approaches positive or negative infinity. If n is even and negative, then f of x approaches negative infinity as x approaches positive or negative infinity. Conversely, if n is odd and positive, f of x will head toward positive infinity as x approaches positive infinity, and f of x will approach negative infinity as x approaches negative infinity. The converse for when n is odd and negative is also true, as shown here. In pre-calculus, we also learned about horizontal asymptotes for rational functions. Given f of x, a rational function, which is a ratio of two polynomials, the degree of the numerator polynomial being n and the degree of the denominator polynomial being m, if n is less than m by any amount, then the horizontal asymptote is at the line y equals 0, which is the x-axis. If n equals m, in other words, if the numerator and the denominator are at the same degree, then the horizontal asymptote is simply at the ratio of a to b, that is, y equals a over b. If n is larger than m by 1, in other words, if n is cubic and m is quadratic, if n is to the 5th power and m to the 4th power, then there are no horizontal asymptotes, but we learn to do long division to find the SA or slant asymptote for this function. If n is larger than m by more than 1, then there are no horizontal asymptotes, nor are there slant asymptotes. The question that comes up then is, can we use the limits, especially limits at infinity, to explain these results, both for polynomials and for rational functions? And can we use limits at infinity to extend the n behavior model to other functions that are not polynomials nor rational functions? And the answer to both of these questions is a clear yes. Let's take a look at both of these in turn. We can examine the n behavior model for polynomials using the limit as x approaches infinity or negative infinity. For an even function, that is, when the lead coefficient has an even exponent, in this case a quadratic function, we can approximate the behavior at infinity or negative infinity using the lead term, the other terms having a minimal effect on the end behavior. We can see that whether we go to positive or negative infinity for an even exponent, in this case quadratic, we're going to end up at positive infinity. Obviously, if I change the sign of the lead term from positive to negative, we would simply reverse the signs of both of these limits. In other words, they would both head toward negative infinity. For an odd function such as 5x cubed, if x approaches infinity, then the limit for the function 5x cubed as x approaches infinity will also be positive infinity. But the limit as x approaches negative infinity for the same function, knowing that if we cube a negative number, the result is negative, we would end up heading toward negative infinity. This is nothing new. This is exactly what we learned in pre-calculus last year. If we apply the limit process as x approaches positive or negative infinity to rational functions, then we should arrive at the horizontal asymptote result that we learned in pre-calculus. For example, if we look at the limit as x approaches infinity of this rational function, where n, the degree of the numerator, is 1, and m, the degree of the denominator, is 3, n is much smaller than m, and plugging in, quote unquote, plugging in, we arrive at infinity over infinity, which is an indeterminate form. The trick with dealing with indeterminate forms of infinity over infinity for rational functions is to find the highest degree polynomial, or I should say the highest degree term in the denominator, and divide all of the terms by that particular degree, that variable. So therefore, we're dividing everything by x cubed in this case. Algebraically reducing our terms gives us 5 over x squared plus 7 over x cubed, all divided by 4 plus 7 over x squared minus 17 over x cubed. Now, if we take the limit as x approaches infinity, we note that 5 over a very large number squared is approaching 0, as would be 7 over infinity cubed. 4 is unaffected in the denominator, but 7 over x squared and negative 17 over x cubed also head toward 0 as x approaches infinity. And the result is 0 over 4, which is 0. This is exactly what we expected from our pre-calculus course, that we would have a horizontal asymptote at y equals 0. We would get a very similar, and in fact the same result as x approaches negative infinity, once again using our modified form of the rational function, and we would end up with the limit as x approaches negative infinity of this function also equaling 0. Again, that tells us that we have a horizontal asymptote at y equals 0. The question that comes up is, can we use the limit as x approaches infinity or negative infinity to non-polynomial or non-rational functions in order to extend the end behavior model for these functions? Here, we're looking at the limit as x approaches infinity of e to the x, and I plugged in to use some bad notation, but I think it is instructive, that if I plug in infinity for x, clearly e to the infinity is still infinity. Likewise, if I plug in negative infinity for e to the x, I end up with e to the negative infinity, which can be rewritten as 1 over e to the infinity, or 1 over a very, very large number. And that limit is simply 0. And this is indeed what we see for e to the x. As x approaches positive infinity, e to the x heads toward positive infinity, and as x approaches negative infinity, e to the x also approaches 0. We can consider now the limit as x approaches positive infinity for the function ln of x. I've written it out here. And for positive ln of x, or positive values of x for ln of x, we will increase toward infinity without bounds, although it would take a while to get there, a while meaning fairly large values of x. Eventually, ln of x does go to infinity, and therefore the limit as x approaches positive infinity of ln of x is infinity. The limit as x approaches negative infinity of ln of x is undefined. And the reason for that is that negative values of x and even 0 for ln of x, these numbers are not part of the domain of ln of x, and therefore that limit becomes undefined. And that's clear from this graph. As we continue our exploration of the behavior of functions as x approaches infinity or negative infinity, sine and also cosine pose an interesting dilemma in that they oscillate between positive 1 and negative 1 forever. Because they do so, these functions, cosine and sine, never converge to any particular value as x approaches infinity or negative infinity. They will just continue to oscillate forever. And so as a consequence, these limits do not exist. Likewise, although tangent has an infinite number of vertical asymptotes, it too never converges to a particular value, and therefore the limit as x approaches positive or negative infinity for tangent also does not exist. But interestingly, if we look at the limit as x approaches positive infinity for the inverse tangent function, well, that is going to actually converge to this upper horizontal asymptote of pi over 2. Likewise, as x approaches negative infinity for inverse tangent, the inverse tangent function will actually approach negative pi over 2. The limit as x approaches either positive or negative infinity of arc sine, also known as inverse sine, of x is undefined. This is for the simple reason that the inverse sine function or arc sine function has a range of -1, 1, and a domain of negative pi over 2 to pi over 2, both inclusive, and therefore do not extend to negative or positive infinity. The same, by the way, is true for arc cosine. It has a very narrow range and domain, and consequently, infinity and negative infinity are not part of the natural domain of these inverse functions. Welcome back from infinity. I hope you learned something about how functions behave at infinity, and I also hope that you're enjoying my rendition of Beethoven's Moonlight Sonata, a piece that seemed appropriate for this background. I'll see you in the next video, but please remember again to subscribe to my channel and to like this video. I'll see you next time.